Hello, my name is Yarolsav Alekseev, and today I would like to give a talk about a lower bound for polynomial calculus with extension rule. First of all, I would like to start with the motivation of studying proof complexity. So one of the main reasons why we study propositional proof systems is that the existence of a propositional proof system that admits polynomial size proofs for all tautologies is equivalent to equivalence between classes NP and co-NP. One of the most famous examples of the propositional proof systems is the resolutional proof system. This proof system is very well studied. There are a lot of exponential lower bounds which are known for proof systems for decades, and many extensions of these proof systems are considered, such as resolution over linear equations or extended resolution. Most of those extensions are really strong, relatively strong proof systems. Moreover, extended resolution simulate extended Frege, where Frege is a very strong logical proof system, and extended Frege is extended version of the Frege where we can introduce the new variables. So it's really hard to prove the exponential lower bounds on the size of refutations for extended resolution proof system. However, in our work, we are going to consider algebraic proof systems, such as polynomial calculus. Polynomial calculus is a dynamic equation of Neustadt proof systems, and the polynomial calculus refutation is a sequence of polynomials where each polynomial are derived by one of three rules. So first rule is that we can say that our polynomial is one of the initial polynomials. The second rule is that we can say that it is a linear combination of some of the previously derived polynomials. And the third rule is that we can multiply our polynomial by any variable. So this proof system is also very well studied. Lower bounds for this proof system are known for probably 2 decades, and it's also interesting to consider extension of those proof systems. So first extension that we will consider in our work is polynomial calculus with square root. The first three derivation rules of this proof system are similar to the original polynomial calculus proof system. However, in our case, we are going to work over the rings instead of fields. And we also add square root derivation rule. So that's it. Also, we should note that in the original setting, the polynomial calculus work over some field. And in our work, we are going to consider that our polynomial calculus with the square root will be working over some rings, such as rationals or integers. And we also will modify the definition, so the constant at the end of our proof can be equal not just to 1, but also to any constant from our ring. Also, we are going to add an extension rule to our proof system, so extended PC square root refutation of system of some polynomial equation is just a PC square root refutation where we can introduce new variables, which encode some arbitrary polynomials, which depends on variables from the original system of equation and on some of the new variables which we introduced earlier. So this proof system is really strong. It's easy to see that if the system P1, etc., Pm equals to 0 is a translation of CNF formula, then this proof system can simulate extended Frege proof system. So it's really hard to prove the lower bound in this case. However, in our work, we are not going to work with the translations of CNF formula, so we actually can prove a lower bound for this proof system. Also, we need to say a few words about the measure of the size of the polynomial, which we are going to use in our work. So in the classic setting, when we are working with polynomial calculus, we say that the size of the polynomial is the number of the monomials in that polynomial. However, in our case, we are going to say that the size of the polynomial is the number of bits we need to encode this polynomial. And the size of the refutation is the sum of the sizes of all polynomials occurring in this refutation. Also, we are going to consider the extension of resolution proof system called Res-Lin proof system. Res-Lin proof system is a resolution proof system which works with the disjunction of the linear equations and have the following inference rules. First rule is the resolution rule, which was modified in order to work with the linear equations. Second rule is just a simplification rule. Third rule is the rule where we can delete duplications. And the last rule that we can derive the tautology expression the fact that our variables are Boolean. So the refutation of some system of disjunction of linear equation is the derivation of the empty set from this system. And also the size of the refutation in our settings is the number of the bits we need to encode this derivation. Now I would like to describe the system of polynomial equation for which we are going to prove our lower bounds. So binary value principle is the following subset sum principle. And also we are going to add Boolean axioms. So the system would be unsatisfiable. The recent result of part Tzameret shows that any Res-Lin refutation of this binary value principle consists of at least 2 power omega of n disjunction, which means that obviously the size of any Res-Lin refutation of this binary value principle should be at least exponential. In our work, we are going firstly, we are going to show that extended polynomial calculus with square root of rational requires exponential size refutations for binary value principle. After that, we will show that this proof system polynomially simulates Res-Lin proof system. And scholarly, we will get that any Res-Lin refutation of this binary principle requires exponential size, which gives us the alternative lower bound. It was to mention a few words about the second theorem, since that in Boolean setting, when we are working with translation of CNF formula, we don't actually need the square root rule, since extended Frege simulates Res-Lin. It's not really hard to show it. However, since we are working on arbitrary system of polynomial equations, we need to prove that our extended PC with square root polynomial simulates Res-Lin. And actually, we will need the square root rule, since we have duplicate deletion rule in the Res-Lin. So our lower bound consists of the 2 parts. In the first part, we are going to show that the constant in the end of our extended PC square root refutation over integers is divisible by every prime number less than 2 power of n, which means that it consists of at least exponential number of bits. So in order to prove that, we consider the constant in the end of our refutation. Let's call it m. And firstly, there is an easy observation that if m is divisible by every prime number less than 2 power of n, then m is divisible by the product of all those prime numbers. And then we know that it consists of at least exponential number of bits, since we can use serial approximation or anything. Then we can consider arbitrary integer such that k plus 1 is prime and k is not negative and less than 2 power of n. And we can consider its binary representation. Then we can consider our refutation of binary value principle. Then we know that there is polynomial calculus with square root refutation in which we have new variables y1, etc., ym. Then we would like to substitute some integer values into variables y1, etc., ym, such that the polynomials y minus q would be zeros for all y's. Then we will prove that our polynomials that we are deriving in our proofs, in which we substitute constants from binary representation of integer k, and also we would like to substitute the integer c such that they make our new polynomials, which we get from introducing new variables into 0. So we would like to show that if we substitute this in our polynomials in each proof line, then each proof line would be divisible by k plus 1. Then it's obvious that the constant in the end, it is a proof line for our refutation, will be divisible by k plus 1. We will do this simply by induction. So in the base case, we will just need to check it, and it's obviously would be true, since all our polynomials would be equal to 0 or to k plus 1. Then we will need to show the induction step. Suppose we know it for first y polynomials, and we would like to show it for y plus 1 polynomial. There are 3 cases based on the way in which we derived our polynomial, and all of those are really simple. So if r is one of the initial polynomials, then its case is similar to the base case. If it's a linear combination, then it's multiplied by some variables, then it's also obvious that our polynomial is divisible by k plus 1, since we are working over integers. And if you use a square root rule, since we know that k plus 1 is prime numbers, then we know that from the fact that polynomial from which we derived by using square root rule, our polynomial was divisible by k plus 1, then we know that our polynomial also divisible by k plus 1. So we know that m is divisible by the product of all prime numbers less than 2 power of n. Then we know that it consists of at least exponential number of bits. Now I would like to discuss the lower bound over rationals. So the theorem states that any extended PC refutation with square rule over rationals of binary value principle requires exponential size. I'm not going to show you the full proof, since it's very technical and not particularly interesting, but I'll go through the main ideas of the proof. So let's discuss the sketch of the proof. Suppose we have some refutation of binary value principle size S. Then we would like to consider all integers then we occur in it. So integers m would be the products of denominators of coefficients in polynomials r. Delta would be denominators of all coefficients alpha and beta, which occur in the linear combination derivations in our proof. So the derivations of the form alpha r plus beta r, something like that. So the main idea is that we can construct the refutation over integers, where the constant in the end is equal to the constant in the end of the original proof multiplied by some product of those constants m or delta. So the proof of this fact is rather technical. All we need to do is to precisely translate each line of the proof, multiply it by the proper constant, and by induction we can get this fact. So It's pretty simple. Then we can show that this product is divisible by, so then we can show that the product of integers m, delta, and r without the powers is divisible by all prime numbers less than 2 power of n. We can delete here powers since we are talking about the divisibility by primes and they don't care about the powers of our integers. Then we know that this product is divisible by all primes less than 2 power of n. Then we know that this product consists of at least exponential number of bits. Also, we know that all of those numbers are written explicitly in our proof, so that we know that the size of our refutation is at least exponential. And that's it. That's all of our proof. So the main fact here is to show that we can construct our refutation over integers, but it's done simply by induction, where we can transform each line by where we can transform our line in the original proof into some line into integer proof, but we just need to multiply by some constant our line as the original proof and carry all those constants through our original refutation and get the integer refutations that we needed. Now I would like to discuss the relation between extended polynomial calculus proof system and the Res-Lin proof system. Suppose we have some disjunction of linear equations and we would like to translate it into some system of polynomial equations in order to simulate Res-Lin in polynomial calculus setting. So the translation would be following. For every linear equation in our disjunction, we introduce a new variable. And also we say that the product of those new variables are equal to 0. Also, if the original disjunction of linear equation was the empty disjunction, we will define its translation to be single equation 1 equals to 0. So the theorem states the following, that if we have some derivation in Res-Lin proof system of some system of disjunction Q1, etc., Qm, then there is an extended polynomial calculus with square root derivation of the ending of the translation of the ending disjunction of the original derivation from the union of the translation of the initial disjunctions. And this refutation is of the size polynomial of the original refutation. Here we should know that if the original system of disjunctions of linear equations was the translation of CNF formula, we don't actually need the square root rule to simulate it. But since we are working over arbitrary settings where we have arbitrary disjunctions, then we actually need the square root derivation rule. So the proof is a simple induction on the number of steps in the original Res-Lin refutation. So we just simulate steps in the original Res-Lin derivation one by one. There are 4 cases based on which rule we are using on the current step. So if we are using resolution rules, then we can easily simulate it, since we can take a linear combination of the products. If we use simplification rule, then we also can just multiply our product by some newly introduced variable. If we have some variable which is equal to some constant which is not equal to 0, then we can delete it. And if we have duplications, then we can multiply our product in order to get a square, and then we can use the square root derivation rule and successfully simulate this step. So as a corollary, we can get that any Res-Lin refutation of the binary value principle requires exponential size, which is an alternative way to prove a lower bound for this instance. And also we should note that the square root rule here is necessary, since there are some derivations which can be easily done in Res-Lin proof system and cannot be done in extended polynomial calculus proof system. My particular example is, suppose we have equation where we have binary value principal squared, and we would like to derive just binary value principal from it. And if you try to do this in the extended polynomial calculus without square root rules, then this derivation requires exponential size. And it's also pretty easy to see that if we have the disjunction of two binary value principles, and we would like to derive just one binary value principle in Res-Lin settings, then we can easily do it by using duplicate deletion rule. So this derivation requires exponential size. In order to prove this, we should just do the same things that we are doing when we was proving the expansional lower bounds on the size of extended polynomial calculus refutation, but we just need to focus on the we just need to prove lower bound over integers and to focus on the constant, which should be multiplied by binary value principle in the end of our derivation. This constant should be very large and should be divisible by all prime numbers less than 2 power of n. And then we just make a translation from the extended polynomial calculus derivation over integers into extended polynomial calculus derivations over rationals. And then we can get our lower bound. So we have some open questions. First question is about square root rule. Is it really necessary to simulate Res-Lin refutations? So we know that if we have square root rules, and we can simulate any derivation which not necessarily ends by empty clause. Also, we know that if we would like to simulate any derivation, then we actually need a square root rule, since there are derivations that we cannot be simulated without it. But if we're talking about the Res-Lin refutation, which means that derivations that ends on the empty clause, then it's an open question about, do we actually need the square root rule? So it is interesting. And another open question is about the size of the constant in the Res-Lin refutations. So from the lower bound of part and Tzameret, we know that any refutation of binary value principle requires exponential number of disjunctions. And from our lower bound, we know that any refutation of binary value principle requires exponential size, which means exponential size of the constant, which leads us to the following questions. Does the exponential lower bound on the size of the Res-Lin refutation, of any Res-Lin refutation, imply exponential lower bound on the number of lines in the Res-Lin refutation, which means can a refutation with a big constant be simulated with the refutations with a small constant, which is also a really interesting question. So I think that's all. Thank you for listening. Goodbye.